Thank you, Filipe.
All right, folks. I'm assuming you can hear me fine. Yeah, this is a Seattle-only tutorial, but it's being recorded. So if you know folks on Slack or virtual participants that want to check this out later, it's also the same tutorial from last year. I was planning on a revamp and a renovation, but I didn't have time. But I wish I was there with you. I wish this so much because I wanted to break out my brand new post-pandemic t-shirt. But sadly, I can't. And if you understand this, I'm sorry, you are a nerd like me.
Where do I get
Anyway.
one? Yeah. Can you send the link to the Cafe Press or whatever?
So let me share my screen.
Oh, yeah. Yeah. You have to add, but because of the screen.
And from this moment on, I lose all your faces. So I'm not sure if you're following or not. Can you see my screen?
You zoom in?
Can you zoom in a little?
Yes. This first notebook is not that important. And you all have that notebook. It's just to explain what a pellet is, because all my analysis is going to be based on plastic pellets. Plastic pellets are actually this nasty thing down here. They can be found on sandy beaches pretty much everywhere in the world now. They are the raw materials to make plastic stuff, from toys to whatever. And they either fall into the sea when you're loading or unloading them from ships, or in some cases, they're actually used to wash oil tankers, for example, like a scrubbing thing. And it's really sad because pretty much anywhere you go, if you start looking at the shoreline, you're going to find them. So this notebook here just shows how we prepare the data. Some folks collected these pellets at several beaches around where we live, photographed them, then we remove the background, and we kind of homogenize the main color. Like this one has mostly a grayish tone to it, so it became gray. And then our data set is pretty much the red, green, and blue of this color here. So this is our data set, but we have like several different pellets. We do have shape, size, and some erosion information on them as well, but we're mostly trying to correlate the color to what is called a yellowing index, which pretty much tells you the age, like for how long that pellet was on the beach. And like the sun usually turns these things yellow the more the sun shines on them, like pretty much any other type of plastic. And by doing this, we want to figure out for how long it has been there. All right. So feel free to play with the notebook, but you pretty much just load the sample and show how we did some image processing to get to our raw data. So let's get to our first notebook. This is a quick introduction to machine learning. They are a brief but hands-on practice and stuff. Last year we did have Valentina's awesome presentation. This year we don't, but you have it synced here, so please check it out. It's really good. And we are going to revise some of the nomenclature and principles from that presentation here. So machine learning will solve our problems, right? Well, actually, I should change machine learning to AI now because the hype just moved. It's always a moving target on the last buzzword. But it doesn't, because it's machine, and we always need an operator and a human. Tomorrow, we're going to see Miranda's awesome tutorial on how to code with ChatGPT, for example, which is a large language model. But just yesterday, I saw some news that for coding specifically, ChatGPT is mistaken 77% of the time. But how can Miranda teach that if it's wrong most of the time? Well, because she knows how to ask the question. She is the operator. She knows how to optimize the question to get useful answers. And it's pretty much what we do in all these techniques. We prepare the data, we understand the data enough to use them in our favor. Otherwise, we're going to end up with things like this, like a hugely big cow, because it's not actually a cow, it's two different cows. Anyway, what is machine learning? So before we start, just some caveats. I'm not a statistician, I'm not a mathematician, I'm not a machine learning expert. I just play one online. You can find my work on movies like how do I get by with little to no data? Oh gosh, the PI wants some buzzwords in the report, or fuzzy logic no longer does it. We need machine learning, AI, or DL. By the way, yes, I'm that old. I remember fuzzy logic. And if you remember too, you should pretty go to the doctor because you need yearly checkups like I do. If you don't, you're a young person, you're fine. So what is a machine learning? A personal point of view. It focuses on practical problems. It learns from the data and makes predictions from it. So the more data, the better your model is. The middle ground between statistics and optimization techniques. It's neither, but it's kind of in between. And now that we have fast computers, we can let the computers do the work, right? Because in the past, we did the statistics to reduce the data because we couldn't crunch a lot of data. But now we can. And there is this awesome talk by Jake van der Pla on how the computer power improves on these new statistics techniques and machine learning. And oversimplified take, you feed a model to the data, it's all a model, and you make predictions. And this concept is so simple that the whole scikit-learn library API is designed around that. You have models, you have fit, you have predict, and you have accuracy tests. Some vocabulary. So we have the parameters. Those are the variables that define the model and control the model behavior. We have the actual model. That can be pretty much any technique that falls on the circle of machine learning, let's say. It's a set of mathematical equations that we use to approximate the data. We have labels or classes. Those are quantity or category that we want to predict. We have features. Those are observations or the information that the predictors are going to be using. We have the training that use the features on non-labels to fit the model and estimate its parameters. So now we just come full circle, right? In our vocabulary. But why stop now? We can throw more fancy words at you. We have the hyperparameters, which are the variables that influence the training and the model, but are not estimating during training. We have unsupervised learning that extract information and structure from the data without training, but with non-labels. We will see clustering and principal components analysis that falls on the unsupervised category. And then we have the supervised category, which fits a model using data to train it, to make predictions on it. Examples are regressions, classifications, span detections, recommendation system. And here we're going to see the KNN, the nearest neighbor classification type. All right, so let's start with an unsupervised method, or the PCA. One of those is called the PCA, the principal component analysis. The data set will always consist of the red, greens, and blues of those palettes, like index for colors. Those are our parameters. And we also have some extra information like the palette size, shape, and etc. The labels that we're going to use is the yellowing index, which is a proxy for the palette age. The goal is to predict the yellowing based on the palette's image broken down to its RGB info. So this is our data set. We just loaded, and we have here the RGB information. This is the palette's name. It's actually the name of the picture, size, overall color, the description, some erosion indexing that we convert to integer, and the yellow indexing that we also convert to integer. I think we have 4 categories to each, like 4 categories to erosion and 4 categories to yellowing. By the way, if you're following along, don't follow in slide mode, because then you can see the code above and below. I'm just doing slide mode here to be a little bit more self-contained so I can focus on one information at a time. We're going to plot some histograms because that's what we do when we're exploring the data. And like we actually have only 3 categories for erosion and 3 for colors. And this is the palette description, and the yellowing we actually have 4. So I have a lot of palettes that are low yellowing index, kind of the same amount of palettes on the moderate and high, and just a few palettes with very high yellowing index. Try to remember this information as we go along, because this is going to be influencing on the technique that we choose and on the results, how we interpret the results. This is the overall color, not really the RGB index. So we have a few that are resemble yellow, some that are white, and some that are transparent. And the erosion seems to be all over the place, but most of them have moderate erosion, some low erosion, some high erosion. Erosion means that it loses its outer shell, and this can lead to confusion because a very yellow pellet, like a node pellet, can peel off the shell and appear perennial, right? So we have a problem that's kind of nonlinear and very complex here. And this is going to throw a wrench in our machine, and we're going to see how this is going to play out as we evolve on this tutorial. Okay, we're going to be using the RGB index data for now, so let's get only those columns. Before we do any sort of analysis, let's take a look at the cross correlation. Of course, each color correlates perfectly with itself, but we see that the red correlates very well with green, but poorly with blue. And green correlates kind of 50-50 with blue. So the first step in most machine learning is to standardize the data. We do not want high variance data to bias our model. So we create something like a z-score, which we do the data minus its mean divided by the standard deviation. And now all the standard deviation for all the data is 1, and all the averages should be 0. This is 0, okay? Trust me. I know computers. Computers can do math. Anyone can explain what's happening here, by the way? No one?
RGBs are only 8-bit or something like that.
It's a floating point operation number, right?
Yeah.
It's very close to 0, but it's never going to be exactly 0. But anyway, it's not that important because this number is really, really small. All right, so this is the beauty about scikit-learn. Pretty much every model has the same API. So we import from scikit-learn the composition, we import the PCA, we start the model, and we fit. So I pretty much started with a number of components known because I want all the components, and I'm fitting on the z-score data. The PCA object, or the fitted model, it was designed before pandas existed. Scikit-learn is quite old. So it's all based on NumPy arrays. But because we can do better nowadays, I'm attaching labels to it. So this data frame here is not the actual output from scikit-learn. It's something that I attached. And we have the principal components in the rows, and we have what we call like time series, but actually time series is the structure of the PCA on the columns. We can project into the data, and we can take a look at our first two principal components. So as we saw with our correlation, red and green kind of cluster together here to the left on the first principal component, but green and blue kind of clusters to the top on the second principal component, right? But they're still far apart on the principal one. They're only close on the principal 2. If we try to see the percentage of variance explained by each component, pretty much the first component explains the whole variance. So maybe we would be okay working with just reds and greens and discard blue entirely. That's the only kind of information that we got from this. So the non-projected loaders plot can help us see if the data has some sort of aggregation. Let's try that out. And I did the non-projected PC principal component 1 versus the 2. And I threw in some symbols there to the yellowing index, the low, moderate, and very high. So we can see that the very high, it's almost completely separate from the rest. We kind of can see the low and the high separate, but the moderate one is all over the map. It's really throwing a wrench in the machine learning here, right? And the reason is, like I said, it can be either low or it can be high or even a very high that was just peeled off. And the color is a mixed bag and we can't really classify it. But at least we could separate the very high very easily. Those are unambiguously easy to separate from the rest. In summary, PCA is probably the most robust and easy to perform non-supervised machine learning technique. And it has been a common technique in ocean science even before the machine learning hype. Even before I ever heard machine learning, I was already doing PCA, and you all probably do. We learned that a single RDB value doesn't have enough predictive power to be used alone, so we need at least 2. And the loading plots show the moderate and low yellowing have some overlaps that can be troublesome when using this sort of techniques for prediction. All right, I'm going to stop here for questions before I go to the next notebook. Going once, going twice. No question? By the way, if I'm going too fast, feel free to stop me, because really, when I'm not seeing faces, I'm just seeing my screen, I tend to talk way too fast. All right, unsupervised learning, part 2, k-means. So we do have the yellow index that we use as truth to access our PCA. But it may contain some sort of operator error because someone looked at those palettes and said, this is yellow, this is yellowish, this is not yellow, right? It was a human that was doing that classification. So because machine learning methods are all about finding patterns in the data without training a model with labels, we can ignore that and check if there are patterns in the data that matching our yellow index to see if our operator is doing fine or if our machine classification is doing fine. So we saw in our PCA that the loading plots of the data may be aggregating in cluster. Let's check a pair plot to see if we can find those in the data. So again, we load our data, we convert our yellow index to integer, and we do a seaborn pair plot. So pretty much here we have RGB and the size of the palette, and we do have the low, moderate, and high, and very high yellow index. If you can see the green and the red, you kind of have some linear correlation and some sort of almost layered, but hard to see connection with the yellow index. And it does repeat a little bit with the size, but the size is actually all over the place. It's pretty random. And the red, the size, the green, the size, everything is pretty random here. And the greens, the blues, we could separate the high, but again, the moderate one is all over the map. So it doesn't seem to have a very, how can I say, obvious classification. So let's try it anyway. In our pair plot above, we can see the RGB size seems to be pretty random, probably no information there. And size, right, the palette size. The R and the green seems to be linear correlated with the yellow index. The RB and G and the G, sorry, the RB and the GMB show some clusterization that may have some predictive power, but I don't think so. Because as you can see, there's always this moderate here that goes all over the place. And we can try the simplest form of k-means. You just need to tell it the number of clusters that we're going to look for. And we're going to look for 4 clusters because there are 4 yellow index. So first we separate our features, RGB and size. And now that we have our features, we start the k-means model. Again, scikit-learn is the we import the technique, we initiate the model has some options, in this case 4 clusters, we fit, we predict, and there we have it. These are the clusters. There's no real information for humans there, so let's get our feature columns and do our pair plot with our clusters now. It seems good, right? Because it does seem that separate things a little bit better. We just don't know how these clusters correlate with yellow indexing because they don't seem to. Like, especially here on the green and the red, if you go back here, I'm sorry, you could see that the low is on this part and the very high is on this part. But if you can see here, you don't see a specific color here. You see 3 different colors along this linear tendency, right? And just 1 color here. So maybe these clusters have nothing to do with the yellow index. But we did get some nice clustering, right? However, they don't really match the data. And if we trust our machine learning 100%, we could say that our yellowing index operator was wrong most of the time, but I doubt it. But there is any way to improve this clustering. And I asked, what are we missing? What is the thing that we didn't do in this data set? Usually when I'm on site, whoever answered these questions get a coffee or a beer later. So I'm gonna ask these questions, but I'm gonna owe you the coffee or the beer. So can you tell me what are we missing? No one? Come on, don't leave me alone here. I don't even know if I'm still connected to Zoom.
Filipe, could you repeat the question? I think some people didn't get it. Yeah.
Okay, so what are we missing in this model? I'm going to get the model here. So we initialize 4 clusters, we fit, we predict. The model didn't really match our cluster that we see in our pair plot. What did we do wrong?
Is it a random state?
Not really, because we use the random state just to ensure we're going to have the same results. But if you check the means, they are kind of all over the place, especially because I have a different unit here when I'm using size, like the RGB at least have the same kind of unit. It's the light index. And we check the standard deviation is even worse, like red and green are close, but blue has way higher standard deviations. So we forgot to standardize the data. And now, instead of rolling our own z-score like we did for the PCA, we're going to be using scikit-learn's own pre-processing model that will come in handy later to creating pipelines. As you can see, I'm guiding you through the process and all the thinking on how to explore the data. I'm not really showing you one technique that gives you the answer. So now we're going to import from scikit-learn the pre-processing module. We're going to start the standard scaler. This is pretty much that equation that I did by hand before. And it works like everything in scikit-learn. You instantiate it, you fit it, and then in this case, you transform. And you can have custom scalars as well, or custom operations here that you can create and add your own equation there. And now that I have my scaled X, I can redo my analysis just to ensure that I have 0 mean and 1 standard deviation. Now I'm going to do my k-means again, and things didn't improve much. Right? I still have like clusters that are going more linearly here along this axis than along this axis as I saw in the original data. So while this does seem closer to our yellow index, ignoring the clusters on size, because originally that was mostly random, it's really hard to make a visual comparison. But now let's say we trust our yellow index operator again, and let's compute metrics using that as the truth. So scikit-learn has the metrics module, and I'm doing the accuracy score where I'm getting my model against my results, and my accuracy is pretty low. It's just 40%. Like, this is really bad for a model. So negative results alert. Even if we just trust our truth, with the yellow index coming from the human operator, our clustered yellow index comparison is terrible. Machine learning is helpful, but it's not a silver bullet. So if you have a werewolf problem, machine learning won't help. Our features are correlated and there is some overlapping. So they may require a different technique or gather more data from a different feature. However, during the PCA and the k-means, we did learn a bit about the data. And we should always start with the simplest model first and check our results before doing something more complex. By the way, these two techniques are also applied on this tutorial here. I invite you to check it because it not only has a nicer result, like they have a positive result, but it also has penguins. They are trying to classify penguins based on shape and size and everything. All right, but we are not done yet. We can try another technique of supervised learning that's called the k-nearest neighbor classifier. So let's say again that we trust our human operator, we trust our yellow index, and we can train the model using those. So the examples of supervised learning always include the linear regression, some sort of vector machines, neural networks, include deep learning. And what they do is they train on the data and then they classify new data. So the simple possible supervised learning model is the KNN. The KNN assign labels to assign the labels based on the labels of the k nearest neighbor. So let's try it out. Again, we load the data. We are dropping pretty much everything here just using the RGB because we saw that the size didn't help much. And now we do our k-neighbor classifier. Again, model, fit, predict. This is the prediction. This doesn't tell us much. But the beauty here is because we are using our labels, it's no longer zeros and ones. It's actually on the same unit down the label that we provided. So let's check our accuracy score. Well, pretty high, right? 82%. That's pretty good for a model. while that's quite the improvement, are we forgetting anything again? And yes, we forgot to standardize the data again. So I did that on purpose, not only because before I want to introduce you to the pre-processing where you could have the standardization or pretty much anything that's related to pre-processing on scikit-learn model, but I want to introduce you to pipelines. So here I did my standard scalar and I redid everything and I have 77 or 78% of accuracy. It's still pretty good, right? Before we were overfitting, that was why we had such a high score, like more than 80%. This is our pair plot. And now I'm doing with the KNN result, but I actually make sure that I'm showing here that I did with the KNN result, because if you have on your mind our regional with the yellow index, you're gonna see that they are very similar. As you can see, we aggregated the low here, aggregated the high here, and we kind of we were able to separate at least those two major categories. But how can we stop forgetting to standardize the data? Like I did this twice on 2 examples. Well, the whole reason I did that is because I wanted to introduce you to the pipeline. Scikit-learn has this pipeline module where you can make your own pipeline and add pretty much all the steps here. So I create a classifier object that's a pipeline that will do the scalar and then the k nearest neighbor classifier. And then I can do fit, classifier, and score, like pretty much 3 lines. And this can be like several layers of several pre-processing or any other techniques, or even chain techniques. All this machine learning that you see in production out there, like even Netflix, they pretty much use this. And it's very robust. And once you nail down your analysis to science, you can freeze a pipeline and apply it to incoming data and always have nice results. So validation, we didn't do that. Luckily for us, scikit-learn has a model for that. So we can use the model selection, the train test split, when we don't tell them the fractions is 75, 25%, if I'm not mistaken. So it's 75% to train, 25 to test. But you can tweak that yourself. And as you can see here, like my train matrix is 95/3 and my test is 32/3. Now I do the fit on the training. I'm no longer doing the fit on the whole data set. And I do the accuracy test on the test, just to check how things are going. And as you can see, my accuracy test change. I actually got a higher score, 78, but you can do the cross-validation score, which does this several times and and can even do shuffling your data, so you can have a more robust estimate by doing the average of all those scores. And our true score is actually 71. So it lowered a little bit. And why did we reduce our accuracy when performing a train test split? Well, we removed data, right? So that means that our model is data hungry. Like we definitely need more data to have a more stable response here. And we definitely want a stable response, because otherwise, if we add more data and we had higher score, we may be overfitting. If we remove data and have a lower score, we may not have enough data. So this kind of cross-validation is always good to try to gauge where you are. But we have another problem. Remember this histogram? Like we have very few high yellow index and a lot of low yellow index. So our data isn't balanced. And to do any sort of unsupervised learning or even supervised learning, unbalanced data can be a problem. So what do we do next? We can try to balance the current data. There are techniques for that inside scikit-learn. We can collect more data and see if the data balance itself out, which could be the case here, or because of the erosion problem that I told you. Or we can choose a technique that's more robust to unbalanced data, and that's usually decision trees. And I'm going to stop here. I actually wanted to go to a decision tree notebook with this data set, but I haven't got there yet. But if you want to do that yourself, that is this awesome paper, and it's pretty easy in scikit-learn. You just stage the decision tree model, and you try to fit on this data, and I encourage you to try that. I'm going to stop here for questions before I show the last notebook, because the last notebook is actually just a show and tell. It's not really part of the tutorial. Any questions?
My question is that do people still use unsupervised learning? And because from what we've seen, it seems that supervised learning performs better, quite better. So are there scenarios where unsupervised learning perform better than supervised learning?
It's really hard to hear you from afar. Can someone closer to the microphone repeat the question or type that on Slack?
You
I
wanna,
apologize. Sorry.
maybe, can you, might come in here? I think it's, or you can speak louder.
So my question is that it seems that supervised learning performs better than unsupervised learning. Are people still using unsupervised learning? And are there cases where unsupervised learning will perform better than supervised one?
That's a very good question. And if I'm being honest, it's more of a philosophical question than the technique per se. The thing is, unsupervised, depending on your data set, and if you're a scientist, you are kind of removing any sort of bias, right, on the data, and it gives you more insight. The supervised one, you need to be very sure about your labels and about your data collection to extract good information from it. For example, one thing that's supervised, and it's the next example that I was going to show, you compute the El Nino or the Southern Oscillation Index, right? And then you try to use that as a label on the anomaly temperature data set to predict the next El Nino. But we are always very sure about our computation of the El Nino index because it's down to a science. It's literally a one equation, one definition, right? But if you're not sure about your labels, like in this case, where the yellow indexing was part of an operator that we don't know how they did it, then an unsupervised technique may be better. So yeah, it's not about one being better than the other. It's more about the problem that you have and the data that you have. Did I make it messy, or did that explain your doubt?
Yeah. I understand that. Thanks.
Any other question? I know there are some machine learning experts there, and this is kind of basic, but if you have a higher level machine learning question, we have Valentina around, and she's awesome. And she knows all these basics and way more complicated stuff. All right, so I'm gonna show the last notebook before I let you go. And this notebook, I'm not the author of it. I was modifying it because I want to show you with new data, but I didn't have time to do so. You can find its origin here and even more nice material on machine learning. But what they're doing here, they're instantiating a TensorFlow model, and they are calculating the El Nino index. That's why I was mentioning this before, because I was doing this right before we started. And when they calculate the ENSO index, they separate the train, the test, and the validation for El Nino and La Nina. So they're going to try to use this data here associated with where it came from on the original data to predict this. And of course, if the model is okay to predict this, it should be okay to predict with newer data. So they are using neural networks. Neural networks is something that I'm not an expert, but TensorFlow and Keras make it seem very, very easy. You just create your layers. I'm not going to get into the details of this. You can look at the original link with all the explanations. I want to show you this graph here, though. As the model iterates, you see the training and the validation converging and reduce the loss and increasing the accuracy. So you could probably stop your iteration around here. And now, well, right here, you can see that this model was able to accurately predict El Nino with 94% of accuracy. What I wanted to do, but I haven't got to it, but this is a nice exercise to y'all, is to change this data to something that goes all the way to 2023 and see if we can predict this current El Nino and its intensity. All right, so let me stop sharing. You all have these notebooks on the Jupyter Hub. You can hit me for any questions on Slack or right now because we do have some free time. But then again, this is mostly like to put everybody on the same basis on machine learning. So some of you may find this complicated, some of you may find this extremely simple. But as long as you understand the basics of scikit-learn, you should probably be able to use it in your projects. Any last burning questions?
Still didn't say where you got the shirt. Where did you buy it?
We like your t-shirt. Where'd you buy it?
Oh, it's a neighbor that does t-shirts. It's not something, I don't buy online stuff. Like I stay away from big box stores and Amazon and etc.
Well, I have a question for everybody. Actually, it's more out of my own curiosity. How many of you have taken a machine learning class of some kind? 1, 2, I'm just, yeah, 1, 2, 3, 4. Kind of like 6 people out of 25-ish. And how many of you have used machine learning of any kind in your research? Oh, okay. And it's interesting, I feel like it's like a disjointed set of people. I'm sure some of you who have taken classes have applied it, but it seems like a lot of people have done it, have not taken classes. And I think most of us are this way too. So yeah, Filipe, you have something to share about, I mean, you applied some of those before, right? And then neural networks started to bloom and you started using it. Do you have any experience to share with folks maybe?
My personal experience with neural networks, and I only use it twice, it's very easy to get the results that you want. So it's a bit dangerous, especially if you have a lot of data. And to me, it's still kind of a black box. I don't really understand the whole math behind it. So if I'm doing science, I prefer to use simpler techniques that I can explain everything that's behind it, that I can actually create my own accuracy checking that I trust, because as you can see, like in the last notebook, we had like 94% of accuracy in that data. And as I was trying to use more data, that decreased very, very fast, which means that it was probably overfitting. And so I can show you one example that's perfect. And as soon as you add an extra month of data, things go south. There is a problem with the model, right? Like, be very careful. Oh, sorry, go ahead.
No, I was just saying, whether anyone has some thought they want to share on their experience.
I guess, like, to follow up on your question of who's done a machine learning class and who hasn't, like, you know, a PCA, for example, like, I feel like it's maybe, like, I could be completely wrong, but I feel like now it's more fashionable to refer to that as machine learning. Whereas, like, I originally would have learned that in a stats or a physics class. So it's a little bit about, like, what does machine learning actually mean? Like, are you training a statistical model? Or is this, like, I think people hear it and they think of like artificial intelligence kind of thing, so.
Buzzwords, right?
Yeah.
I think we have this cartoon of, I think Valentino, you might have shared a cartoon of, maybe you can describe it verbally.
Yeah, well, I don't know what it is, but it was basically a stat column and machine learning column and the stats term and the corresponding machine learning term. And the last row was salary and the stat salary was low and the machine learning salary was high. You get it. But yeah, a lot of the things are the same, it's just a question of how people call them.
in one context, using this machine learning phrasing gives you an advantage, and in another context, people are gonna for not to hear about it, so. You frame your science in a certain way, you see papers with the name of the model in the title, but they avoid using the word machine learning. Buzzword that. But in the end, it is a statistical model under the library. Math is just not something we can go through on one piece of paper, but it is math under there.
Yeah, I guess I wouldn't don't really think of PCA as machine learning, just because there's an analytical solution. And I think when I think of machine learning, I'm thinking of cases where I have a lot of parameters and that many parameters that are kind of partially related. They're not orthogonal, so they're not correlated with each other. And I am using an algorithm that's going to navigate this space and make choices about what parameters to include. And there are kind of an infinite number, or there's a very large number of ways that it could include those. I guess they're calling it features in the model. And my machine learning is exploring this very large space. And this is kind of part of the problem, why there's not one solution. Or with PCA, it's an analytical solution. There's, I can change what data I give it, but the data set, there's going to be one solution.
I'll not say what that is or isn't machine learning, but I would say that what you just described is a good use of machine learning, right? Because the PCA will reduce the data. It's still a machine learning technique and you can still use in that problem, but once you reduce it, you need to be sure that whatever you found is significant to what you're looking for. But if it's not, then yes, you should go to the next step, which is what you just described. And that's definitely a good use of machine learning techniques to look into a multi-space parameters that it's so messy to reduce it that you can't reduce it. You definitely need to look from different objects.
Well, I'll just say one important thing is to actually try different methods and compare the performance. And you only can pick one complex one and one simple one and compare. And that's the only way to know which one is better instead of hypothesizing before that whether it could be a good method. You can try and compare. And then, you share in your paper. I tried this and I tried that. This one is good. Don't worry about the names. You try several things. Whichever works doesn't matter.
I think I'm going to stop the recording. See if I can get stopping the project.
Sounds good. Thank you.